Alrighty, howdy everyone. Welcome to another week. Hopefully everyone realizes it's Wednesday. And how did our quiz go yesterday? Is that why we're here? Okay, cool. Well, that's just the first quiz, right? So one quiz does not define who you are as a chemist. And you do get to drop your lowest quiz out of the 6 you have this semester. So we'll just push that one to the side. If you're not going to keep it, it's okay if you aren't. We'll just make the next ones better. But if there's anything that you need to review with the quiz, there's still people that need to make it up and take it. So we can discuss that next week or at a later time, once your quiz will become visible to you. They're not going to go over the quiz in class, but you will be able to review your answers so you can see what questions you got wrong. If you want to meet with me or the professor, just let them know and we're happy to help you once everyone has taken it. Any questions about that? Okay, cool. Okay, questions for me. How are we feeling about material so far?
I think I understand that some of the choosing, but with more so mixed them, like you have to understand more conceptual. I know there's the perspectives, for example, I know you can't go over the question directly, but maybe there's like a question that was the table of percentages, which is something we've done in class. But then you had to break to like atoms or something like that. Something different. And purple question. So
Like combining the stuff that you've learned already. Okay.
I thought whenever we went over like combustion reactions, like balancing in class, that was kind of.
Okay.
kind of explained.
Yeah, absolutely. So we can kind of do a little bit of like balancing equations and then kind of play into what the quiz was just on, just so that we kind of review a little bit of that. Is that okay? Is that something where to go? Yep. Okay. So when we're talking about combustion reactions, oh, that's a lie. There you go. All right, so you have combustion reactions. What is a combustion reaction? What are we doing in that sense? Right, we're setting something on fire. What does it do in terms of like the chemicals you're using? What are your reactants usually? Yep. So, right, you're exposing a hydrocarbon. So that's going to be something that has carbon and hydrogen, right? Hydrocarbon. Sometimes it'll include an oxygen, sometimes it'll include a nitrogen, right? There's other stuff that it could also have, but for the most part, it's going to be something that's just carbon and hydrogen. And you're going to burn it. And so you're going to expose it to an excess of oxygen. If we just have this combination here, what are our products when we burn our hydrocarbon? Good, we get CO2 and H2O. Okay, those are always your products when you do a combustion reaction with the hydrocarbon, okay? The important thing about a combustion reaction is that all of the carbon that you see from your original starting material ends up in your CO2. All of the hydrogen from your hydrocarbon ends up in your hydrogen, in your water on the product side. So if you can collect the carbon dioxide and you can collect the water that's produced from this combustion reaction, you can figure out how much water or how much grams of hydrogen you have, which you can then convert to moles, which then you can then convert to whatever, right? You can figure out how much of that you have in your water, which directly relates to the hydrogen that you had in your original starting product. The same thing for carbon dioxide, right? If you know how much carbon you have, then you can know how much carbon you started with, okay? So that's the point of combustion analysis, right? We are looking at an unknown sample and we're trying to find the empirical and then also maybe the molecular formula as well, okay? Any questions on what a combustion reaction is? All right. When we are balancing combustion reactions, an example that we can start off with is this one. What does it mean to balance our reaction? What has to be equal in that case? Good, your products and reactants. You can look at that arrow and say, okay, we're going from reactants to products, but that's also like an equal sign, right? You can't create or destroy matter. So all of the stuff that's on the left-hand side also has to be on the right-hand side, right? You're just converting one thing to another. You're not getting rid or adding anything to the system. So looking at this reaction, is it balanced? No, how do we balance it? Right, so there's not really like a set way that you have to balance a reaction. I tend to work left to right in this case. So usually I'm going to start with my leftmost element, which is going to be carbon here. How many carbons do I have on my left-hand side? You have 3. How many do I have on my right-hand side? You have 1. What are we going to do in order to balance our carbons? We can add a 3 as a coefficient in front of our carbon dioxide. So now this turns into 3 carbons. What about, right, so that's going to do our first element. I'm then going to move to the hydrogen. How many hydrogens do I have on my left-hand side? You have 8 hydrogens. How many do you have on your right-hand side? You have 2. How are we going to change that? We can multiply by 4. So we can have a 4 in front of our water molecule. Does that get us to 8 hydrogens on the right? It does. When we added our 3 and our 4, what did we also manipulate? The oxygens, right? So I'm going to tend to work left to right, and I'm going to say, okay, I balanced that first 2 elements there. Now let's look at what I manipulated, right? I know I manipulated my oxygens. How many oxygens do I have on my right-hand side now? And where did that come from? Awesome, right? You have 3 times 2 here, and you have 4 oxygens here. So we have 6 plus 4, which is going to be 10 oxygens. How many do we have on our left-hand side? 2 oxygens. How are we going to balance that? With a 5, right? We know that oxygen's diatomic, so we just, for every 2 oxygens molecules, right, we have 2 oxygens within those. So this changes this to 10 oxygens, and that's all balanced that way. Questions on balancing this equation? This is how I tend to work on it, right? If you have 2 reactants and 2 products, I tend to move left to right, do that first reactant, see what I manipulated on my right, and then go back to the left. When you're talking about combustion analysis or combustion reactions, when you're balancing them, more often than not, if you have a odd number carbon, you're going to be able to manipulate your oxygens fairly easily. If you have an even number carbon, usually you have to do a little manipulation where you're multiplying by 2 in some cases. So for example, let's take a minute and let's balance this equation. You can work with someone around you, by yourself, check answers, but let's take 2 minutes, work on this one.
like, burning gas in a car would be considered combustion.
Mhm.
Then what's the propane for?
It does, it just is hot and releases that steam.
It's like,
Mhm. That's why you have to keep your engine cool.
highway.
I don't know the chemistry behind that. I feel like that's more atmospheric chemistry. Um, mhm. Alrighty, how do we do balancing this equation? Right, so what did we do first? If we're looking at, right, if we're moving left to right, what are we balancing first? Carbon, how did we do that? Yep, multiplied by 4 on our right, bless you. Then we're gonna balance our hydrogens. What do we need to add? A 5 in front of what? Yep, a 5 in front of the water. Right, and this might set off some flags, some red flags right now. Right, anytime you're gonna multiply something in front of the carbon dioxide, you always are going to have two oxygens in the carbon dioxide. So whether it's an even or odd number, that's always gonna stay even, easy to divide by 2. It's the odd number in front of water that's going to create problems, right? When we add a 5 in front of water, we're only adding 5 oxygens. That doesn't equate well when you have a diatomic molecule on your left-hand side. But if we were to look at this and we're going to say, okay, how many oxygens do we have on our right-hand side? How many total do we have? We have 13 total. So we could just say 13 divided by 2, but they need to be whole numbers. So we're going to multiply everything by 2, right? Kind of just like a fraction in math. Not kind of just like a fraction. So then you are left with 2C4H10, 13O2, 8CO2, and 10H2O. Okay, do we see how we did the balancing for the even number carbon versus the odd number carbon? Okay, any questions? Yep. Yeah, it'll always end up being balanced. Yep. Because you can't create or destroy anything. So whatever you start with, you also have to end with. It just will be in a different form. Yep. Alrighty, so let's look at an example of something we can do with this. So I guess before I do that, the whole point of combustion analysis equations, right, is to figure out what your starting materials are. So from this, right, it's not just balancing equations. You're also going to have to do a word problem with it. So that's going to be the next portion that we're going to do. And you usually have to find out what that starting hydrocarbon is. Okay, so as you're writing this down, I'll read it. So you say you have a 0.250 gram sample of hydrocarbon undergoing complete combustion to produce 0.845 grams of carbon dioxide and 0.173 grams of H2O. What is the empirical formula of the compound? Okay, so what's the first thing you're going to do with this question? You want to set up an equation. Do we know what the formula for our hydrocarbon is? We knew it's CXH, right? We know that there is carbon, we know that there is hydrogen, but we don't know how much of it. What else do we know? We know it's combustion, so we know it's oxygen that is going to be on a reactant side. And what's being produced? CO2 and H2O. Okay, what else are we given from our question that's useful? We know the mass of carbon dioxide, we know the mass of water. So from our mass of carbon dioxide, what can we get? We can get how many moles of what? We can get how many moles of carbon dioxide we have. How are we going to do that? Good, we can use the molar mass of carbon. I'll tell you that 1 mole of carbon dioxide is 44.01 grams. How does getting to moles of carbon dioxide help us? We can figure out moles of carbon. How many moles of carbon are there in 1 mole of 1 mole of carbon dioxide? There's 1. I'm going to encourage you to use your units more than you think at this moment, just so that you see how things are canceling out, right? We know that we have grams of CO2 that are going to cancel out on the top and the bottom. And we know that moles of CO2 are going to cancel out on the top and bottom. So we're just left with moles of carbon at the very end. So we end up with 0.2. 0.0192 moles of CO2. Oh, sorry. Yep. Thank you. Okay, what are we going to do next? We're going to do the same thing for our hydrogen. Your molar mass for H2O is 18.02 grams. How many moles of hydrogen do we have per mole of water? We have 2 this time. Right, and here's a case where hydrogen's a diatomic molecule, right? But you don't have 2 moles of H2, you have 2 moles of hydrogen, right? That's the difference here. You're not using your diatomic for this conversion. You're just saying you have 2 H's. Yep. They're just saying in their natural state, they are a diatomic element. Yep. Right, because 1 mole of H2 is different than 2 moles of H.
It's not possible to find H just in like H group.
It's not impossible, it's just not as common as H2. right? And we're left with 0.0192 moles of hydrogen. If these weren't the same, what would be our next step? You want to divide by the smallest. In this case, right, we can still divide by the smallest. It just happens to be that they are both the same. So what is our ratio of carbon to hydrogen? It's 1:1. So what's our final empirical formula? CH. Okay. So let's write out what our reaction would be. And let's take a minute to balance this equation. The smallest amount of moles that you have. Yep. Alrighty, did we balance this equation? What did we get? Okay. Let's walk through how we did that. So the first thing I'm going to look at is my carbon, and I see that I have one carbon on both sides, which means I'm then going to move to my hydrogens, and I see that I have one hydrogen on my left-hand side, but on my right-hand side, I have two. So instead of having two on my right and one on my left, I'm going to put a 2 in front of my CH because I know, right, that I have to have those balanced. So if I change that, I now have 2 carbons and I have 2 hydrogens. But now I screwed up my carbons on my right-hand side. So now I'm going to put a 2 in front of my carbon dioxide. That changes that. Now all of that is balanced. And then I'm going to look at my oxygens. And I have 2 oxygens on my left. And I have 5 oxygens on my right. So in order to balance that, I would have 5/2. But I can't have fractions. I'm going to multiply everything by 2. And we end up with 4 CH, 5 oxygens, 4 CO2, and 2 H2O.
Do you think that you could do balancing at the?
Any questions on this one? I'll do that in a second. I'm gonna
Yeah.
do a couple little pieces. Any questions how we balanced this equation? Alrighty, in our original question, we said that we have a 0.250 grams sample of our hydrocarbon, right? So we have right? We have a 0.250 gram sample of CH. How many atoms of hydrogen are there? How do we solve this question? Perfect, right? We need to take our grams and we need to get into moles. So we have 0.250 grams of CH. We have to get to moles. So what are we going to use in order to get from grams to moles? We need to use our molar mass. What's the molar mass of CH? 13.02, right? So for every 1 mole of CH, we have 13.02 grams of CH. Are there? Yep. Right, so we convert from moles of CH to moles of hydrogen. So how many moles of hydrogen are there in 1 mole of CH? It's 1, right? We have 1 mole of hydrogen for every 1 mole of CH. And how do we get to atoms? Then we need to use Avogadro's number. Where are our numbers for Avogadro's number? And what's our unit on this? Atoms of what? That I don't know. I don't know the experiment behind it. I'm sure he weighed a whole bunch of stuff until he figured it out.
Like a dozen, or just like some side things.
And like he might have just decided that too. It has to deal with carbon, so I'm sure he did a whole bunch of experiments with carbon.
What kind of experiment?
I'm not versed in the experiments he did. I know other experiments, but not this one.
What is the chemistry going to be?
Yeah. I would love to meet Watson and Crick, because they came up with Watson-Crick base pairing of DNA. And then the woman who took the picture of the first DNA helix, that Watson and Crick end up stealing for data from. I'm a chemistry PhD. Yep. All right, so we end up with 1.1559 times 10 to the 22 atoms. How many sig figs do we need with this? 3. So what's our final answer? 1.16 times 10 to the 23 atoms of H.
which means we're not able to count.
Nope, so those are just conversion factors, and all conversion factors have infinite sig figs.
Okay, so that's why we're just taking off the 6. Off of 13.0 to.
Nope, so what number are we basing it off of for our sig figs? The 0.250 grams. So that's something you had to weigh, that's a measurement you had to take, that's where your significance comes from.
So when we, like, our 0.250 has 3 sigfigs, when we get like the molar mass, there are periodicity is like 5 sigfigs, we have to chop that, or do we just chop?
Nope, you just use whatever's given to you on your periodic table, because those also have infinite sig figs. Right, those are known values at this point, so, they don't count towards your sig figs, it's just the measurement you're taking. Yep. Oop, sorry, yes. So if you look at, right, your molar mass of CH, you have 13.02 grams in 1 mole. We know that 1 mole is 6.02 times 10 to the 23 atoms. How much are we starting with? 0.25. So do you start with less or more than a mole of your molar mass? You start with less, right? So you're expecting your final answer to be less than 1 mole of atoms because you're starting off with less moles of atoms. Right, so that's always a good check for that one. Right, I think the best thing you can ask yourself as you're practicing your chemistry questions is, does this answer make sense? It comes into play a lot later on too. So, right, if we're looking at this, right, my check was I have less than a mole of mass compared to my molar mass, so my number of atoms should be less than a mole, and we are less than a mole here. So this answer does make sense. Okay, so do you see how we started off with a combustion analysis question and we ended up at atoms? Yes, does that help combine a little bit of that? Great. Okay, so then I was asked to do the combustion of ethanol.
How come it's like original food deal? Why see just
Yep, so when you draw, it's 3, I'm missing. So when you draw this out, this is just showing the connectivity. So this is showing you that you have a CH3 like this. And then a CH. And then an OH. So it's just showing you like how it's connected. And then you can also write it like this. And that's the same. Alrighty, so ethanol is this here. We're going to combust ethanol. So this is something that you can see, right? This having a hydrocarbon with oxygen as well, right? You do have some examples where your compound has carbon, hydrogen, and oxygen in it. This is one of them. It can still be combusted. If you want to balance this, sometimes it is easier to see this all condensed. So how many total carbons do we have in ethanol? We have C2. How many hydrogens? H6. How many oxygens? 1 oxygen. Okay. So how are we gonna balance this? We need a 2 in front of CO2. A 3 in front of H2O. How many oxygens does that give us? 7. So we're gonna do 7 halves in front of our O2. Oh, that's a lie. How many oxygens do we have on our left-hand side right now? We have 3, right? So how can we balance that? We can just put a 3 in front of O2, right? That gives us 6 from our oxygen. And then we have that 1 from our ethanol. So that's 7 right away. We don't need to do anything with the 7 halves. Okay, do we see how those can still be balanced and everything? To help, yep.
Yeah, so is that like the 3 patterns of like combustion are like the carbon will start off even or odd and then. So like you like either multiply by 2 or it's like easily goes and then this one or like you just add a number.
Yep, and basically all of your balancing equations are gonna be the same that way. You'll get into more where you'll have like, it's not gonna be hydrocarbon, oxygen, and then carbon dioxide and water. Some of my extra practice has like actual reactions happening that are just more than this. So then you get a little bit more practice of counting how many of each you have. Yep. Any other questions? Okay, how are you feeling about combustion analysis? Does that help a bit? Okay. Thanks. Anything else we have questions on that we want to see?
I know you don't have it this way, and you maybe go over like last week. Or like the chapter, like chapter 2, part 2, and chapter 3, part 1, and 2, those were big confusion.
Like molarity and stuff? Yeah, yep. Okay, so if we're talking about molarity, what does it mean, molarity? What is that? It's mole over liters. And what do we call this? If something has a molarity, it has a what? It has a concentration. Right, so if we're talking about concentration, that means we have a solute and a solvent. We have a solute, what is this? Usually a solid. What does that solid do? Right, this is usually the thing that gets dissolved. And then we have a solvent. What is this? It's the thing doing the dissolving. Okay, I like to remember this because solute has 6 letters and solvent has 7 letters, so you need more solvent than solute. Okay. Molarity can come usually from something, right, from a solid getting dissolved into a liquid. So, right, something I do in lab often is I have to make 5 molar sodium chloride. Right, so you have, gonna prepare 500 mils of 5 molar sodium chloride. I wanna know how many grams of sodium chloride I need to weigh out and while I'm in lab. How would we go about solving this question? Right, I need to know how many moles of sodium chloride I have. So I have 5 molar, which I always write out as 5 moles over liters. Assume it's moles over liters. Yep. If I want to get to moles of sodium chloride, how am I going to get just to moles? Good. You want to multiply by your volume, right? Liters is a volume unit. If we have 500 milliliters, we can convert that to say that it's 0.5 liters. So I'm going to take my 5 moles over liters and multiply this by 0.5 liters. Mhm.
Can you explain more why you multiply the moles and the liters?
So we are taking our concentration of 5 moles per liters and we're trying to get rid of the volume component, right? We're trying to say how much mass or how many moles of sodium chloride do I have within my volume. So in order to get rid of the liter component in molarity, we're going to multiply by volume. It's the same thing as saying moles over liters times liters over 1, right? They're going to cancel out that way. Does that make sense? All right, so how many moles of sodium chloride do we have? We have 2.5 moles of NaCl. How many grams of sodium chloride am I going to have? How do we get to that? Now we need to go from moles to grams. How do we get from moles to grams? We need to use our molar mass. Is grams going to go on top or bottom? Going to go on top. 22.9. Should know that one. So how many grams of sodium chloride do we need? Yep, this would be 4.6. For this one, I'm like, it should technically be 1. So I gave you 500 with no decimal point. So, but for the sake of being accurate in lab, we will go for 4. Questions there on just general molarity stuff. Right, and so you can do the same thing going backwards. Right, so that's one thing, right? You're going to do a question with me. If you're studying later, look at the questions we do during class and see if you can work backwards. So if I said, okay, I gave you 100 grams of sodium chloride and you're preparing 500 mils of this, what molarity do you have? Right, so now you're changing differently, but you're starting with grams and have to get to molarity and see if you could do it that way. Okay. Any other questions on molarity or this one here? Okay. The other thing with molarity is looking at things like magnesium chloride or aluminum nitrate. Yep.
We're given, of course, we know from the periodic table like 2 elements each of their grams or their atomic weight, but then we take more compounds and we get like the percent that you would compose it, you have to solve.
Absolutely. Okay, so we have magnesium chloride as a solid and we have aluminum nitrate as a solid. If we add this to water, right, we're going to hydrolyze it and make it dissolve. What is that going to do in solution? It's going to break apart into what? Right? It's going to break up into its ions. So we're going to have magnesium. And does anyone know the charge on magnesium? 2 plus. And how many chlorine ions do we have? 2. What's the charge on chlorine? Minus, right? So, but we have 2 Cl minus ions. Right? We do not have a Cl2 ion, right? That's not an ion. An ion has a charge. It's breaking up into its charged particles. What about aluminum nitrate? What does that break up into? Yep. What's the charge on aluminum? 3 plus. And how many nitrates did we say we had? 3. Yep. So this is just saying aqueous, saying that it's dissolved. Okay. If I had If I had 1 mole of magnesium chloride, or 1 molar, excuse me, magnesium chloride, how many molar, what's our molar concentration of magnesium in solution? 1 molar. What's my concentration of chlorine ions? 2. If I had 2.5 molar aluminum nitrate, what's my concentration of aluminum? 2.5 molar. What's my concentration of nitrate? 7.5 molar. Okay. When you do that in your head, right, you said 2.5 times 1 is 2.5. And you said 2.5 times 3 is 7.5. That's what you're doing with all of your conversions, with all of your dimensional analysis. It's just icky numbers at that point, right? You're using your coefficients in order to find the ratio of your starting to your final products. I just made that up.
When you say molar, you say like molarity or
Molar is molarity. Yep. Right. So that's 1 molar solution. And that's the capital M. 1 mole is the little m or MOL. Good question. Yeah, you'll be given your solubility rules as a reference sheet. I think you keep your polyatomic ion chart as well, so you'll get all of that. Okay, does that make sense with what's going on here? Okay, so then same thing that we did above, right? You can find how many grams of things are, right? You can get to moles of things if you're looking at combining solutions or anything, right? You can find the common ion in between those based off of the molarity or the molar concentration here. Okay, I do think I have a couple of those for my week 2 practice that I put on at the very end. So if you want to look at those, that's some extra practice there as well. Okay, and then let me get a question. right? So for this one, we have a compound is found to have 64.8% carbon, 13.62% hydrogen, and 21.58% oxygen. And we want to know what the empirical formula is. How do we go about solving this question? Mm-hmm.
From that. Or 7, 6, 7 hydrogen, 1, 5, 8 oxygen.
Perfect, right? So we have a percent composition of our compound. We can assume that, right, all of these have to add up to 100%, so we can assume 100 grams. That way we can say that 64.80% carbon means that we have 64.80 grams of carbon. We have 13.62% hydrogen, which means we have 13.62 grams of hydrogen. And then the same thing for oxygen. Do we like working in grams in chemistry? Nope. So what do we have to do? We have to convert to moles. Okay, so we're left with about this much of each of them. What do we do from here? Right, divide by the smallest. Same thing that we did in our previous empirical formula with the combustion analysis. We want to divide by the smallest number of moles. Which one's our smallest? The oxygen. So we're going to divide by 1.349. Okay, we get 4, 10.096, and 1. Do any of these need to be rounded or multiplied by something to get a whole number? Yep, so we can round hydrogen down to just 10, right? 10.096 is close enough to 10.
Sometimes it's like 2.5 something. 6 something.
Yep, so we'll finish that in a second. Right, so if we have 4, 10, and 1, are those all whole numbers? Yep, so we can say that we have C4H10 oxygen. And this is our empirical formula. Okay, if you have something that is 0.25, what fraction gets us 0.25? That's 1/4. So you're going to multiply this by 4. If you have 0.333, what are you going to multiply by? You're going to multiply by 3. You have 0.5. What are you gonna multiply by? 2. You have 0.667. This is also gonna be 3, right? That's 2/3 instead of 1/3. You can multiply by 3 there. And then if you have 0.75, you can also do 4. Anything else you can either like round, right? If it's below 0.25, then you can round down to the nearest whole number. Or if it's 0.2, right, you might want to try multiplying by 5. If it's 0.2 times 5, and that will get you to a whole number. Yes, yep. All right, so if this was 4, 10.25, and 1, what would you have to multiply by? You have to multiply by 4, so everything is multiplied by 4 in that case. So then what would carbon turn into? Yep, you have C16. H41. O4. Questions there? Okay, this is your empirical formula. If I were to ask for the molecular formula, what do you need in that question? You need the molar mass of that compound, right? They said, what is the molecular formula, assuming that it's 192 grams, right? You're going to take the empirical formula and divide and use that to divide your molar mass by your molecular mass by your empirical formula. So the molecular formula divided by your empirical formula. And that should get you how many times you need to multiply your empirical formula in order to get that one. They would give you the molar mass. Yep. So
And then divide.
no. If I were to say that this compound has a molar mass or a molecular weight of 222.4 grams per mole. What's your molecular formula? Right, so I'm going to say molecular formula. You're going to find the molecular formula or your molecular weight, your molar mass of your empirical formula. C4H10O has an molar mass of 74.1, I think. So then you're going to take 222.4 divided by 74.1. And what number do we get? Yep, we get 3.00134, which is about 3. So what do we need to do to our empirical formula? Multiply everything by 3. So then our molecular formula becomes C12H30O3. Yes, yep,
74 came from the mass.
yep, that's 4 times 12 plus 10 times 1 plus 16.
Your compound's like 3.
Yep,
So why can't you just put a 3 as coefficient?
because then that's saying you have 3 C4H10O molecules. But your molecular compound has 12 hydrogen or 12 carbons, 30 hydrogens, 3 oxygens.
Because you have
Yes, right, but it boils down to the same empirical formula. So you can have the same empirical formula for multiple molecules, but you only have one molecular formula.
for different molecules. They have the same empirical from the different. They have the same thing.
So kind of, right? One thing that we saw is that you can have an alkane, which is just a single bonded molecule between your carbons. So these all have C2N plus H2N plus 2 formula. So you can have CH3, you can have C2H6, you can have C3H8. All of these boil down to the same empirical formula, right? Even C4.
CH3 and C2H6 are really very different substances.
Yes, right. So CH3 is just, I'm sorry, this is CH. That's fine. It's whatever. Right. Those are going to be very different. One of them has 1 carbon, one of them has 2 carbons. If you keep going up, your C10H22, right? This is going to be very different than this, right?
They're the same.
But they have the same empirical formula. Yep, and that's why the molecular formula is the one that matters. So, right, this compound here is going to be more solid at room temperature than your C2H6. It has stronger like intermolecular forces and stuff and a higher boiling point. So very different, but same empirical formula.
Why is it covalent, right? Ionics are always simple.
Yes, yep,
So that means we can't exactly tell, like if we're given 2 empirical, if from the empirical one, we can't like 100% tell what that substance is.
correct. Okay, does that help with chemistry this week? Yes, okay. Alrighty, well, it is 6:34. I will let y'all enjoy the rest of your Wednesday. If you have any questions, please let me know, and then this was recorded, so I'll post this along with any notes that we took, latest by tomorrow morning, but hopefully tonight. Yeah, thank y'all. See you next week. Say that again. Yes, yep.